Welcome to the new lecture. In today's lecture, we will discuss about a scheme which is called cooperative relaying. Cooperative relaying schemes are basically an extension of MIMO systems. MIMO systems are basically multiple input, multiple output systems in which the transmitter has N antennas and the receiver is supposed to have M antennas, and which makes multiple channels. The need for multiple channels is that we can send different data on different channels, and that will lead to what is said to be the spatial diversity, or what we spatial multiplexing rather. And if we can send the same data on different channels, then it will increase the reliability. It will generally increase the probability that the information will reach the receiver, and this will increase the diversity. We can also have beam forming scheme in which we steer the beam of the antenna towards the user that we intend to transfer, and therefore we increase the diversity. And the final one is actually cooperative relaying systems, where multiple devices actually work in cooperation. So cooperative relaying techniques are basically, it intends to basically utilize a device that is already existing user in the system. The device of the user is used. Due to this, there is no increment in the requirement of hardware. We can understand that in MIMO systems, we require multiple antennas, and multiple antennas lead to increase in hardware. So, if we can use an antenna of an existing user, the device of the user in the wireless communication system, then that increases the efficiency of the system and reduces the requirement of hardware. Due to this, the capacity of the system can also be increased, the coverage will increase, and this will actually lead to diversity and multiplexing gain depending on how we use it. So, how do we implement these cooperative relaying techniques? The basic principle is that there is said to be a source node which wants to communicate to the destination node, but it's not communicating directly. Right? There is also provision of a direct link, but suppose that there is no line of sight. So if in case of an NLNOS communication, it transmits through a node that is said to be the relay node. So therefore, there are basically two hopes the communication takes place. The first hope is said to be source to relay SR link, and the second hope is said to be RD, which is relay to destination link. Since it takes place in two hopes, this system model is said to be dual hop. You will find this in research work, dual hop relaying, right? So since there are only one relay and therefore two hops, you can also have multiple relay nodes to make it a multi-hop communication system. The first hop is said to be the source to relay. The second hop is said to be relay to destination, and the relay node hardware is of a different device. This means that this basically the relay, the antenna on this relay node is basically coming from a different user, and therefore it's not increasing the burden of hardware on the transmitter itself. Rather, it's increasing the diversity using an antenna of a different device. This is where these three nodes cooperate with each other, and therefore the name cooperative relaying systems. Depending on how the relay operates, it can either be amplify-and-forward or decode-and-forward. If the relay node receives the signal and simply amplifies it, since it just amplifies, then it comes under the first category. The first category is said to be the AF relay, and this is very simple in operation. It is rather less efficient. The simpler it is, the less efficient it becomes. You can make the system more complex, and it can basically decode and then encode and then again encode, right? And if this happens, then this comes under the category of decode and forward relaying, which is complex, but the performance is better. Now, I have in this engineering knowledge channel under the playlist of wireless research, I have discussed the wireless system signal flow, and I will just quickly summarize that because I want to derive the SNR for amplifying forward relaying. So basically, we have already established that there is a wireless user that needs to connect to, suppose, a BTS over a channel which is having AWGN component, which is denoted, the information is X, the fading is H, and the noise is N. and the signal received is y. So if the y signal is received quickly, y is given as h into x plus n, where basically h is called the feeding coefficient, the narrowband approximation of the channel. You can see my links in this comment section, and you will find that all this has been discussed in previous videos. And h and n both are random in nature. Based on this, we calculate what is said to be the signal to noise ratio, which is the most important performance metrics for wireless communication systems. So it is basically the ratio of signal power upon noise power. We generally denote it using gamma. So if I look at this equation again, we will have that this component here is basically the signal part. The signal is inside the fading, so h into x, and this means that the signal power is basically expectation of mod x square and h square, because these are basically voltages. So power is voltage square, and therefore the power is square of the voltages. Similarly, the noise power, it is random awgn we assume, and therefore we take the variance of this as the power of the noise. Having said that, the now signal to noise ratio can be defined as signal power upon noise power. So gamma will be expected value of mod x square, mod h square. Mod h square is h square is the fading channel coefficient, mod square upon sigma n square. So this becomes my signal to noise ratio. Now, since we now know this, we can go back and derive the signal to noise ratio for amplified forward relay. Let us go there. So we have a source node. It wants to communicate through a relay node to the destination node. The first link is said to be the SR link, which is source to relay link. Where it uses to send the information symbol X over a channel having a fading coefficient, say H1, and the signal that is received at the relay node. Suppose power P1 was used, P1 power was used. This is power. So if P1 power was used, the equation will become H1 into X plus N1. You can follow from my previous discussion and previous videos. And square root of P1 just means that the power is P1. So we want to square something to make it power. So therefore, in voltages, I will write it as square root of P1. So this is the signal YR that is received at the relay node. Now we are talking about what strategy? We are talking about amplify and forward strategy. So what it will do, this is the signal received at the relay node, है ना? And this basically is the AWGN component. So what basically the relay will do, relay will take this wire, the signal received at the relay node, and it will provide it some amount of gain. Depending on what gain it provides, there are multiple variants of amplify and forward relay. Now next, the destination receives the signal over the relay to destination link, that is also called RD link. So over the fading coefficient, which is H2. So this signal YD is, suppose I will omit this root P2. So please eliminate this. So you'll use H2. H2 is the basically fading coefficient on the RD link, and GYR is basically what? This is the signal that is coming at the output of the relay node. So output of the relay node multiplied by H2, plus suppose then there is an AWGN, additive byte Gaussian noise component N2. Now if we go further, if this H1 is same as H2 and not equal to, basically we mean to see that they are uh, the distribution is same, the random distribution, the stochastic distribution underlying H1 and H2. If they are same, then the system is said to be symmetric relaying. If H1 and H2 are not same, means they are not, one is Rayleigh distribution, other one is Nakagami distribution, Hessian distribution, K distribution, log normal distribution, exponential distribution, you name it. So if the two H1 and H2 fading coefficients on SR and RD link follow different distributions, then we say that these systems are basically asymmetric relaying fashion. Now, if we talk about the various types, so that type of AF relaying system can come on the basis of the gain that is given. So first of all, my received signal, if you understand, was square root of P1 H1 X plus S1. This was at the relay node. And at the destination node, basically what happens is that H2 is the fading coefficient G multiplied by YR. So this complete entity, what I have written is YR, right? Plus N2. So this is my YD. I can expand this. I can expand it to write uh, H2 of G square root of P1 into H1X, the first two components, and second two components, H2G N1 plus N2. Now from here, you can understand that now what happens to the signal to noise ratio. The signal to noise ratio is basically signal upon noise. Where is the signal? Understand this. This was the symbol that we want to transmit. So basically, this component is signal. The first component is signal, and the second component is noise. So if I do that, this is signal and this is noise. This complete entity is noise. So if I draw the signal to noise ratio, I have written this earlier also. So this will be mod h2 square. Mod h2 square is coming from this component, g square, because again I have written g. So square of g will be the power, and square root of p1 square is p1 and mod h1 square. So this basically is the signal power, right, in the numerator. And in the denominator we will have elsewise. So from the second components, from this space we have the denominator, right? So sigma n square, because I am assuming that the AWGN component variances are same on H1 and H2. This is on SR and RD links. This is a fair assumption. It generally violates no contradiction. And the mod H2 square will be from this entity, and G square. So this will be and plus sigma n square from here. So this will give me sigma n square. So basically the noise component is coming in the denominator, and in the numerator we are having the component of signal power. So signal power upon noise power is what we have established, and that we refer to as the signal to noise ratio. Now what I can do, I can take this G square common, and in both the terms. So this G square and this G square, I can take both of them common, and I can rewrite this expression like this. I can take this G square here. Now, depending on G square, we have multiple types of AF relaying systems. Suppose I am giving one example, and this is just arbitrary to tinker what is already existing in the literature. The gain that the amplify and forward relay gives to the system is based on what happened in the first hop of communication, SR link. So if SR link equation was YR is equal to square root of P1 H1 X plus N1, it only knows these things. Understand this. So it can give a gain based on these things. Suppose it gives a gain like this. It gives G square is equal to P2 upon sigma n square. So it is taking, I, and this is where I will give a question also at the end of the video. But suppose I am assuming this, and I want to make this substitution in the above SNR equation. So this means that it is giving a fixed gain, and there is no CSI. No CSI means that it is having no information of what was the fading coefficient on the first hop of communication on the SR link. If this is the case, I can substitute this G square in this expression. So what it will become? It will become, you can see, and I can also, and I have written it. So the numerator remains the same. Denominator is mod h2 square sigma n square plus sigma n square upon G square it was. So it will become reciprocal of G square. So it will become sigma n square upon P2. I can take this P2 and multiply here. So I can take this P2 and I can multiply here, and it will come also in the numerator. So it will become like this. It will become P2 mod H2 square, P1 mod H1 square, P2 mod H2 square, sigma n square into sigma n square. Now these two sigma n squares basically means that it becomes sigma n4. It becomes sigma n4. Now what I can do, I can divide this complete numerator and denominator with this sigma n raised to the power 4. If I do that, what happens? So in the numerator I will have upon sigma n square, and the denominator I will have sigma n power 4. So sigma n power 4 has been tackled like this. I have written P2 mod H2 square upon sigma n square as the first component, and second component as P1 mod h1 square upon sigma n square. So sigma n raised to the power 4 has been consumed in the numerator, and in the denominator I am taking it as common, so it will become p2 mod h2 square. Sigma n square was earlier there, and in the denominator it is sigma n raised to the power 4. So you can understand that this will be cancelled and this will become 2. This has become 1, and this is the trick. So when I have done that, now I will have the final and the most important expression of signal to noise ratio for amplifying and forward relaying systems. So I have already written the same equation that I established in the last slide. I will define two SNRs. So first SNR is my gamma 2. Suppose gamma 2 is P2 mod H2 square upon sigma n square. The second SNR is suppose gamma 1, which is P1 mod H1 square upon sigma n square. If I say that, then you can understand that this component here is basically gamma 2. This component here is basically gamma 1. This component here is basically gamma 2, because you can understand that this has already been cancelled. So if I do that for amplify and forward fixed gain relaying systems, I can write, because of my gain that I used, I can write the overall SNR to be gamma 1 gamma 2 upon gamma 2 plus C. Now, this is where one thing that I have left for my viewers to study research papers and come out with. The general expression that is always given everywhere is basically gamma 1 gamma 2 upon gamma 2 plus C, and there is a constant C. So you have to see what happens to the gain of the fixed gain amplifying forward relaying systems in those papers that gives us this signal to noise ratio expression. I will make a part 2 of this video where I will derive the end-to-end signal to noise ratio for variable gain amplify and forward relaying systems. So do also watch that video, and there you will have some idea to how to derive the SNRs on wireless communication systems, which will help you to conduct mathematical analysis on cooperative relaying systems. So this is all what I am going to discuss in this lecture. Thank you.